Despite the 60 seconds of technical difficulties, I do promise that I'm going to present you an action-packed and efficiently paced talk that should get everyone on the road out to Pearson soon enough. I would have said before rush hour, but I feel in this city there are a few hours left on the roads that are not rushed. So do your best, and I want to talk to you today about a couple things. I mean, I have one of these extremely dense academic titles, which I would argue kind of like broccoli is full of good things but difficult to digest. The systems that I'm going to be talking about today are in fact hybrid, in that I'm going to be using both organic semiconductors and colloidal quantum dots. And I'm going to be using them both because I can achieve with the two of them performance that I can't get with one material or the other alone. They're both excitonic systems, and so that's something that's been a bit of a theme throughout the conference, as opposed to maybe a traditional bulk inorganic semiconductor. Those concerns aren't relevant at room temperature. And I want to accomplish something which I'm going to call non-coherent SWIR, or shortwave infrared visible photon up and down conversion, which, I mean, a bit to my surprise, I've had plenty of introduction to so far this week. All right, so first, I want to talk about this photon conversion processes, and in particular, and with apologies to Mr. Floyd, talk about what this process isn't, although we've had a few introductions, and including just one from Vivian, about things like spectral splitting, and so spatially decomposing the broadband spectrum from the sun to allow better efficiency through some sort of multiple junction geometry or multiple optically parallel junction geometry. What I want to talk about are procedures that allow us to juice the performance of a single junction solar cell. And the kind of laser folks in the room will recognize, you know, one of the most obvious. Is there an issue? More mic. Can people at the back hear me now? A third time's the charm? Wow. So I said some things. And I said particularly that I'm not trying to split the spectrum, decompose it spatially coming from the sun to get better performance. I'm trying to actually change the color of photons. And I have, you know, a glamour shot from the Pomfret setup I built back at Cambridge, where we really have red photons coming out from the top right and blue photons coming out from the bottom left. And this is taking advantage of the nonlinear susceptibility of really any non-centrosymmetric material to make new colors. And I think anyone who's given public talks will know that the degree to which people are amazed by this varies non-monotonically with their experience in physics. I find that kind of kids don't see the interest to it, whereas undergraduate students are in the middle of having their high school understanding of what a photon might be turned upside down. Whereas we experts just see it as that trick that make green laser pointers work and don't get as excited as I was like. So really, I am changing the color of photons, and the reason I'm doing it, the reason I want to connect it to photovoltaic energy, is that we have, you know, the standard AM 1.5, and this is a graph that's scaled in terms of spectral energy density, so the area of things on the graph or how much energy we're harvesting. And so the blue area gives you an idea of how well an ideal solar cell with a band gap of silicon would do in harvesting the light. We get some of it. As you all know well, a few direct processes which take us down from Carnot type to Shockley Queisser type efficiencies are the fact that we can't absorb any photons that are below the band gap of the cell, and we waste much of the excess energy of any photons that come in that have more energy to the band gap. And so there are two kind of complementary techniques that we can use to win back a little bit of the energy that we're losing. On one hand, it is up-conversion. So this is the idea of taking two low energy or two or more low energy photons and generating a high energy photon, so that, you know, hopefully we can then couple this into the solar cell and recover some of that energy. And we see this as additional photocurrent. We would, you know, if we could do this perfectly, speaking in the hypothetical, get about a 25% boost in the photocurrent of band gap energy silicon electrons. The complementary process is down conversion, which is, on the other hand, splitting high energy photons. So we save some of that thermalization loss by generating additional carriers. And again, in the hypothetical case, this would give a similar boost in performance. But the issue is, while the processes I introduced on the previous slide are very efficient, the nonlinear susceptibility, or the higher order susceptibility of most materials, is pretty weak. And you only see appreciable efficiencies when the intensities are relatively high. So we frequently do that with a pulse laser, or maybe with a very clever and extremely monochromatic source. But generally, it's not very efficient with non-coherent or thermal radiation, and particularly it's not efficient if that radiation is broadband. And so there are a variety of strategies that for example, Professor Beck introduced yesterday, or that Professor Ferry was just talking about, that allow us to try to do something a little better with these kind of diffuse light, or diffuse in time light. And so, really, the title says most of it. If you want to get one of these processes to be efficient, you need something, some intermediate state, to temporarily store the energy of one photon while you wait for the energy of the other. I mean, it's really addressing the fact that all these involve multiple energy packets being in the same place at the same time. And so as was introduced, a lot of this work has been done with kind of lanthanide doped crystals, where you can find some transitions that give you an interesting ladder of states, and you can kind of ratchet pump your way up as you absorb excitation that's absorbed by the ytterbium, and end up emitting some single high energy photon. And you can do this, and this certainly works, but one of the issues is the exact physics that keep these states isolated from the environment also give them very low oscillator strength. So frequently these transitions are quite narrow and fairly weak. And so, we want to try to do something different. And we want to do something different with our excitons. And so this, I'm sure many of the people in the room lament that the usual textbook definition of excitons begins and ends with the case of a bulk inorganic semiconductor. Here, the Coulomb attraction between the electron and hole slightly modifies the energy of the carriers forming a bound state, but this perturbation is very small compared to KT at room temperature, and so this physics doesn't usually manifest in something like silicon until you get relatively cold. I want to introduce two other systems, and the ones that I mentioned that are referred to as exciton, whether for good or for ill, and that stretch that definition in two different directions. The first are colloidal quantum dots, or nanocrystals. So these are materials that certainly coming from the Alex Santos group, people are very familiar with. These are synthesized in solution relatively easily, and I really want to emphasize that. I mean, I do not present myself as a state-of-the-art, cutting-edge synthetic chemist, but even engineering physicists like me can make device-suitable quantum dots that emit throughout the infrared at kind of a 10-gram scale. And, people who are following closely the Consumer Electronics show this year would show that Samsung seems to have switched to gallium nitride quantum dot displays for their large panel technology, following the lead of Sony a couple of years ago. So there's lots of fun things you can do with them, and the reason we call them quantum dots is because these are now so small that you can actually tune the energies of the lower-lying electron states by confinement. It's a classic particle-in-the-box type picture to capture much of the physics. And so you can get these wonderful rainbow diagrams. This was something taken in Munji's lab, and there are only two different materials used to make all of those different kind of grand aliquots, cadmium selenide and cadmium sulfide. So we now have a semiconductor that is solution processable, readily available, and we can pick the band gap as we'd like, if we at least make the bold claim. So I want to, on the left, put the usual absorption spectrum of a quantum dot, and you can see that there are a number of transitions. These are actually distinct electronic transitions. So quantum dots are intermediate between molecules, and bulk crystals we have a countable number of states near the band edge that matter. If we keep track of these electronic states and make the excitons, which are optically active, you can see the different features that come in. What I really want to emphasize that we don't see in this diagram is the fine structure of any of these states. And this is something that was worked out primarily in the 90s, where the splitting between the spin states, and I think I have this on the next slide, between the lowest lying spin singlet, spin triplet states is much less than KT at room temperature, and the spin mixing process is relatively rapid, on the order of 100 picoseconds. I know I'm an ultra-fast guy at times, but I want to say that in this case, 100 picoseconds is rapid because the radiative lifetime of these systems is tens to hundreds to even thousands of nanoseconds. And so any excitation that comes in is very likely to end up with kind of very poorly defined spin before it emits. Now, I know I showed you a big line of states and that sort of thing, but I can say that vibrational relaxation from higher excited excitonic states is pretty rapid in these systems, and so for most practical device purposes, we can replace the whole band structure of quantum dots with a single two-level system with an exciton with mixed spin. You put something in, it's kind of triplet, it's kind of singlet, it's probably going to emit, and it lives for a little while. I want to draw the contrast with organic semiconductors, something that many people in here know very well. And here, again, we have a number of states, but usually it's only the lowest lying electronic state that matters. And here the spin physics matters. The fine structure is far from fine. Glossing over a ton of details, the general rule of thumb is that the splitting between the lowest lying singlet and triplet is about 700 millielectron volts. So in any system, you always have at least two relevant excitonic states that differ by spin. All right, so I want to review here. I mentioned this idea that we want to motivate with making a better solar cell, the idea of doing photon up-conversion and down-conversion. There are a bunch of ways to do it. I want to do it with excitons, and I've leadingly introduced the fact that the spin physics matters a lot in the organics and doesn't at room temperature in the quantum dots. And so taking the case of down-conversion and speaking in the particular, really what we need to do is figure out how to split an exciton. And from Akshay's talk yesterday, I think you have a little bit of the lead, and the phenomenon we exploit is this singlet exciton fission. So what I mean by the singlet exciton fission is simply splitting one spin singlet exciton into a pair of spin triplet excitons. And so here's the usual energy landscape, and I'm going to pick this system, for example, tetracene, where the triplet has less than half the energy of the singlet. So the first question is, why doesn't the singlet relax directly to the triplet? And the answer, as you all know, is it does, but this is spin forbidden. It's very difficult. You need a spin flip to change between the spin singlet and spin triplet manifolds. This process is generally slow. In fact, if you wanted to design a material with very little intersystem crossing, you would pick a planar molecule with no lone pairs and no heavy atoms whatsoever. And so these ones really do fit the bill. So we'll turn this off, and we'll now consider the fission process. What if we have more than one molecule? What if we have two available states? Fission creates triplets in pairs, and the pair is key, because now the two triplets can be globally in a spin singlet. It's an entangled state. And so we remove the need to flip a spin, and this process can be very fast. I'd like to point this out in this audience that the original report of singlet fission, even though they didn't mention it, was a Canadian paper. This came out from NRC in Ottawa in 1965. And this was followed by kind of a little flurry of papers in the late 60s and early 70s where people worked out these physics in organic molecular crystals. However, the interest reigned. You can see on the right that there is this necessary spatial piece. You need two available triplet states. You need two molecules. And so I feel it kind of came to be thought of as a bit of a curiosity of fairly difficult to fabricate organic molecular crystals. The other trouble is, as I mentioned, the oscillator strength of this triplet is truly vanishing. And so it was very difficult to study with the kind of fluorescence-based techniques at the time. Two things really led to the renaissance of studies in fission. One is the boom of all things organic and solar, had people looking at evaporated polycrystalline films. And the other one is the advent of transient absorption type spectroscopies allowed you to experimentally access a lot more of these non-emissive states. And so this effort included, well, this particular researcher as well as Akshay, who on the two of us showing up in Cambridge, we were given the task to figure out why the external quantum efficiency of a pentacene-60 solar cell was so anomalously high. And to summarize the business in the last 5 years, what we really found is that far from being an unusual phenomenon, singlet fission proceeds relatively efficiently in almost any film, so long as it's exothermic. We had this work that Akshay highlighted came out of MIT and that he contributed some of the transient spectroscopy, where we looked at a bunch of derivatives and found that you could determine the rate or calculate the rate quite accurately from just the molecular structure and some DFT, and that it did not require the presence of some conveniently placed CT state for superexchange or some sort of crazed delocalization, that this is just a straightforward process. And maybe we shouldn't be too surprised, because the inverse process of triplet annihilation is well known. All right, so what are we going to do with this? Let me get this to advance. We want to do down conversion, but the issue is once we've gone, absorbed and created our singlet, and then created our pair of triplets, we need to get them back out. And so we need to couple them to an emissive species, something that's been mixed and something that has the right band gap. I'm sure you know exactly where I'm going. The answer are quantum dots. We now have something that we can tune the band gap by making it of a different size, and the states in there are spin mixed so that they are able to absorb the triplet state. At some point it becomes a singlet and then has a chance of emitting. All right, so to do this, we fabricated a bilayer film. It's really a very simple device geometry with lead sulfide quantum dots and the organic semiconductor tetrazine. You pick tetrazine as it's really one of the canonical fission materials, and it's one that we understood quite well. In addition, its triplet energy is 1.25 eV, or about a micron, so it's quite suitable for trying to couple it eventually into silicon. You'll notice that the heterojunction is type 1, and so this really shouldn't generate charge from the low energy triplet, which is kind of stuck here between the homo-lumo and the organic. And so what we do then is I'll show on the top right the excitation spectrum of the emission from the dots. And so what you can see here in purple is that you can see the characteristic absorption features of the tetrazine alone coming from the emission you see from the dots. It is very clear that there's energy transfer going on. But what I'll tell you is it's not obvious that this is the exciting triplet energy transfer, the Dexter transfer that Akshay was talking about yesterday. This could just be more infrared signals. And so I'm going to present 3 pieces of evidence to try to convince you that it's triplets that are transferring in this system. So the first is we do the transient spectroscopy, and you can see there in the yellow and the orange 2 control methods. These are basically a film of dots alone with their photoluminescence decay and short-wave infrared, and then a film that is a bilayer that is excited with a laser that only excites the dots. And they decay in some sort of way that is characteristic of these laser exchange films. In blue, you can see what happens to the decay when you put the organic on top. In fact, you see a lot more light coming out of the film at later times, implying that there is energy being transferred to the dots to produce this additional emission hundreds of nanoseconds after excitation. From what we know about the organic, there are no singlets left on that timescale. So it's certainly leading that we're transferring the triplets. There's a much more elegant experiment that we were able to do. This is by looking at the magnetic field dependence of the steady state emission from these bilayer films. And so from this work in the 60s, we know exactly what that dependence should look like. You kind of get this characteristic little bump and curve. And this, to make a long story short, comes from the fact that the magnetic field perturbs the number of triplet pair states that are in equilibrium with the singlet, that have fractional singlet characters. So you're just changing the number of states during the partition function. And so anything that has a hump and decreases as you turn on the field is associated with the triplet population. Anything that increases the singlet population. On the top, this is the steady state emission from 4 bilayer films made from dots of different sizes. For dots where the energy transfer is downhill, we see this characteristic signature of triplets. That means when we make there be less triplets in the organics, we see less emission from the light. This is very consistent with triplet transfer. When the dots all of a sudden have too large a bag gap to accept the triplets, all of a sudden we see a weak opposite behavior. Here we've probably turned off triplet transfer, and this is just the weak residual threat of singlets. The fact that this happens at exactly the threshold energy that we expect for the triplet exciton is really highly convincing that we know what we're doing and this is behaving as expected. But as in most things, the best proof is probably the most simple. I want to return to the excitation spectrum, and here we're using a series of ligands. So we start with the leic acid, which is a native ligand that is put on the dots to solubilize in during synthesis, and we then can exchange it to shorter carboxylic acids down to acrylic acid, which is the 10-carbon flavor. So down here what we've done is we've normalized the excitation spectrum of the film by the absorption spectrum. This is a relative quantum field. So out here where only the dots absorb, it's 1. It doesn't really matter where you pump the dots, they're going to get equal probability. With long ligands at short wavelengths where the tetrazine is expected to absorb, it's worse. We actually see the organic shadowing the dots, and so you're now wasting excitation. So as we shorten the ligands, all of a sudden it becomes dramatically more efficient to pump the organic than to pump the dots, and that's to create photons coming out of the dots. If you work this out, this requires that the kind of product of the fission, the triplet diffusion, the transfer efficiency is 180%. So this really is quite efficient. Now, Akshay mentioned that distributed Dexter transfer process and that the spatial dependence should be exponential. We do observe, if you do the ligand series, that it is exponential. But what's weird about this is exponential with a spatial time constant of about 10 carbon bonds, which is an order of magnitude longer than is usually seen for electron transfer processes. To be perfectly honest, we don't understand this yet. Now, I can say that this comes from the efficiency as opposed to the rate. So you could imagine some sort of scenario where there's a competing process that gets turned on the decay channel as you make the ligands relevant. But what I think this speaks to is that most of the processes that we're dealing with here, we have triplet excitons, we have infrared quantum dots, are very slow, and so you don't have to have something that's terribly fast to make it highly efficient. I can assure you that this is under continued investigation. All right, so if we can do down conversion with this system, we can start with one high-energy photon and end up with two low-energy photons. The question is whether we can do the opposite, which is perhaps a little more interesting. And not to jump entirely to the end, but the photo on the right is a bilayer film that's being excited with an infrared laser and glowing happily at 610. So, whereas in the other case we had to do a lot of work to prove to ourselves it was triplets transferring, as soon as you see it glowing and visible, we knew we were doing it right. So to speak about this a little more carefully, we have this schema on kind of an energy landscape where we have the sensitizer, which is a lead sulfide nanocrystal. This is now again in the bilayer film with an organic, and here the triplet annihilation is happening in rubrine. So we are absorbing photons into the dots, transferring those excitations over the triple states to the rubrine, having them find each other, combine or annihilate to create one high-line singlet and then an end. One of the things we learned is you get a lot more efficiency if you dope in a laser dye essentially into the rubrine, and this is in a gas post system. And this is something that was known from the OLED work. Our follow who we're working with is very familiar with this sort of thing. And the idea is you're basically shutting off the back channel, that you're draining singlets out of the rubrine via fret to proximal dyes. And so to speak about this a little more rigorously, here we have in dark blue the emission spectrum of the rubrine, and light blue the emission spectrum of the film. We do lose a little bit of energy, a few tens of millielectron volts, but we get a 34 increase in performance by putting the dye, so we're happy about that. And even with that, from the center of the largest dots that we've been able to get this to work with, we are going 800 millielectron volts uphill, and we're doing this from the infrared. And I think much of this, well, certainly for triplet annihilation-based up-converter is a bit new. So one of the questions always about this is how efficient is it? There we go. And you'll note that the triplet annihilation process is bimolecular, so it will vary with the excitation intensity, so long as there is some competing monomolecular channel. However, once almost all the triplets are finding each other and decaying via annihilation, this then goes first order and becomes independent. So there are two numbers that are quoted. We quote the efficiency at this intensity-independent regime, and then we talk about the threshold where we get there. The title has it all. Right now with our best system, we're getting 5% conversion efficiency at 100 seconds. And so to give perspective, as far as we've seen, the kind of lanthanide-based systems that have been mentioned, I think a record for infrared conversion is around 23% at 800 seconds. So right now, our efficiency is not there, but we seem to be able to get it at relatively low excitation densities. And I'd even argue right now these are very thin films, and so this is this kind of cute scale on the top. On the bottom we have the power density, which is this kind of 100 and 1,000 sun sort of thing. These only have an optical density of about 0.1 right now, so really very little of the light is being absorbed. So maybe we have more to go. And so to understand why we seem to be able to get reasonably efficient up-conversion at such low densities, we did the transient spectroscopy to try to figure this out. So this is, again, the decay of the infrared emission from the quantum dots. Doing quantum dot things, and even though there are some fast processes up here, we see that we kind of plateau into, whoa, I got very excited. I slipped my finger on the laser. There we go. It kind of resolves itself to a very nice long exponential decay. The time constant is 2.5 nanoseconds, or 2.5 microseconds. This makes sense with what we know about the photophysics of this quantum dot in solution. And the stuff at early times is probably transferred to dead dots or any damage that we've done to the dots when we're passing them. We would love to get rid of that, and that is certainly on our list. So we can compare this to a film where we now have the organic on top, which is a sink for the triplet excitons. And you can see the quenching is obvious. We are absolutely vacuuming out excited states for the quantum dots with the organic film. However, at late times, it does asymptote to the same, and they really do mean the same behavior. That's the same, this is the scale data on top, and they really overlap. And so the simplest model for this is we have in our devices a substantial fraction of the quantum dots that aren't talking to anything. And we have some information from, for example, doing AFM in the films that we're getting some kind of SK growth of islands, and so our coverage isn't perfect. So one of the things we learned from this is really the most near-term goal for efficiency is just to get very clean monolayer films, and we're going to be working on this. From this, we can also talk about the rate of transfer in the system, and essentially you just do the subtraction of the scaled copy of the dots only decay, which should take into account these non-participating dots and then the ones that are being quenched, and you find that the transfer dynamics happen on a 400 nanosecond timescale. So that's clearly fast enough to kinetically compete with the kind of band edge decay processes, but it's really rather slow, and this is happening through oleic acid ligands, which are kind of 18 carbons thick. And maybe I'll put on my competitor hat with Akshay and mention that we don't think that the dots are bare, at large naked. You know, the data we took before we did a series of ligands and we found this clean exponential dependence suggests that, well, the ligands are sticking out as you expect. So we're continuing to be amazed at how well these things seem to transfer over such large distances. But just to wrap up, I mean, we see this quenching behavior. This could be happening from anything, we'd be killing it. The obvious one is to do the opposite side and look at the visible emission. And I can tell you as an ultrafast spectroscopist, this experiment pained me a little bit. You can see the timescale on the bottom is tens of microseconds, and I want to convince you that data is not flat. And in fact, if we subtract the background, the processes here are so slow that we have a considerable steady-state population even when we're running at 100 kilograms. And so if we subtract that and kind of look at it, you see the rise, you see the fall, you get rid of some laser scatter, and you see a very consistent timescale, which is lower when we go at extremely low excitation densities and asymptotes to the kind of timescale we see on the other side. So we really do think this matches, that the quenching we're seeing is happening because of the transfer to the rubrine, and that once we have a sufficient density, the annihilation and diffusion is relatively fast. So we think it's going to work. All right, I'd like to just finish by acknowledging many collaborators, particularly Dan and Nick, whose kind of device legwork, incredible device legwork, has made this possible, as well as Mark Baldo and Muji Buendi, who have become my co-supervisors for mentoring an incredible amount of assistance with this project. So I hope I've convinced you that maybe we have a new system on our hands here that can do this incoherent or non-coherent photon up and down conversion, and I'm actually really excited to keep pushing this forward to see where we can go. Thank you for your attention.
Do you have questions?
These quantum dots, when you have a regular acid.
Sorry, photon.
Well, the quantum dots, when you have a oleic acid, this long voltage gets wrapping around the quantum dots and that gives you the product.
So this is a field of debate and not one that I am personally expert. I mean, the people in Paul's group have done a lot more work on this. I think the usual consensus is that they largely stand up. And so there are some hundreds of oleic acid on every dot, and to a reasonable approximation, most available sites are filled. It gets a little odd on kind of the facets of the corners of the dots, and I think that's to be determined. But I would think of it as kind of a hairy bowling ball, with it sticking out kind of in a mess in most directions. And for example, when you put a film of these, the average center-to-center spacing is what you would expect from the dots being extended, as opposed to being interdigitated.
There was another. See, when you treat inorganic material, what kind of statistics do you look for other than the band gap?
So, I mean, for me, I want that it's very synthetically easy, and I can tell you that lead sulfide is a dream to make as opposed to some of these other systems. The band gap is right, and then there's also the kind of ionization energy. So you want to make sure that you have a type 1 heterojunction as opposed to something that's going to dissociate charge. And then lastly, you want it so that present synthetic roots yield nanocrystals with high quantum yields. And right now, kind of the intersection of all of those demands end up with lead sulfide. There's a lot of work on other systems, particularly something like indium arsenide, which a bare dot has quite low quantum yield. If you put a very thin inorganic shell, which is possible, it gets much better. And we're looking at using other systems to see whether we can win.
Okay. The second thing in my mind is that when you have the nanocrystal, they have many top assets.
I mean, that they have facets is true. I'm not sure what, I mean, for people coming from a traditional semiconductor, it continues to be astonishing that something that's almost all surface can be essentially defect-free from the perspective of its emission. And that is just one of the joys of quantum dots with these organic, or even some inorganic ligands. Exactly the physics of the surfaces, which ones are presented depends on things like the size, it depends on the stoichiometry of the dots. Do you have a little extra lead, do you have a little extra sulfur, and that's an active area of research.
Fascinating talk. Would you comment and compare and contrast similar processes occurring in nature and learn from them as well?
So on the fission thing, there is an interesting tie-in that a lot of corroborate molecules, which are not far from some of these like high-risking ones, undergo fission, and it can be argued it's a photoprotection mechanism, a way to get rid of high-energy states before they damage something. In terms of nature, I'm thinking of kind of Greg Scholl's layers of pond scum as one of the ultimate tandem or multi-junction solar cells. I don't know. I don't feel very bio-inspired in what we do. I don't maybe have the biological background, but I think there's certainly plenty here that we can work with. I mean, you could talk about the Z scheme or Z schemes, I should say, in Canada, for photosynthesis, that you need 2 photons to get one of these higher energy states. And so that would be another perhaps comparable direction if you wanted to do something like lots.
Yes. So what happens when you're injecting the triplets from the quantum dot?
Yeah.
Why do you do that?
Frankly, because right now, we don't end up with more efficient devices with shorter ligands. The penalty we pay in reducing the quantum dots from the carboxylic acid ligand exchange, which is a little harsh, is greater than the advantage we get from reducing the transfer time. We have ideas about how to maybe do that a little better. So, but it's exactly, and from the rates it kind of makes sense. I mean, right now, if you have a 400 nanosecond transfer, you have a 2.5 microsecond lifetime, and you should be getting 80–90% just on a simple kinetic comparison. And so maybe that's not the dominant thing if by doing the exchange you introduce a lot of very rapid non-radiative channels on the dots.
You try to force it.
Yes.
Can you check through the force?
It hasn't worked yet, but we're not done.
Any other questions? Let's thank Mark once again.